B part 4, lecture 22, Euler Lagrange and Spatial Translation, stationary path. You see, three previous videos I defined what means stationary path. You see, you just go there and see what it is. Now, you see, I compare the proof of Euler Lagrange and the proof of the conserved momentum. You see, total momentum. So, first, to prove Euler Lagrange, what we did, we consider all tiny variations of epsilon I of t. Also, from there, we got the equation of motion for stationary path. Stationary path is a necessary condition for you to set delta S is equal 0. You see? And this is implied the equation of motion, which we used on this lecture about Noether theorem. And in parallel, proof of dp of dt is equal 0. This means that p is constant. So first here is different from here, because here we considered a teeny time dependent space translation. This is in this case is a subset. This is much more general. You see, this is the teeny variation epsilon I of t. But there is a restriction here. So this is considered all teeny time dependent space translation. This is equal epsilon 1 is equal epsilon 2 of t. Now then we got the conservation law. dp dt is equal 0. P is a total momentum. So the time derivative of p is equal 0. We got that. Then we conclude for stationary here, the stationary, then you set delta S is equal 0, and also this implies that P is equal constant. P is a total momentum. This is conserved momentum. When the particle moves, the momentum is conserved when you set spatial translation. We considered spatial translation. See, that's very important for you to understand the difference in the derivation of the Euler Lagrange and the spatial translation, assuming a stationary path.